sources. That's the concept we're going to be playing with as we go through this chapter. Okay. So let's start real quickly with a refresher. We actually worked this problem last week when we introduced the electric field, but let's just do it again. So I have these two charges, a positive charge and a negative charge, and I want to know what direction does the electric field point at this point in space away from these objects. So let me go ahead and launch the poll. All right, 10 more seconds and we'll close the poll. Okay, so let's go ahead and end the poll. So most of you said that the answer was D, this vector that's pointing to the right. Okay, let's convince ourselves here. If I draw a line that runs from this positive charge up to that point that I'm investigating, I know that the electric field at this point points radially away. Okay, so the electric field coming from that positive charge points this way. For the negative charge, I can draw a line that connects that point to the negative charge. I know electric fields point radially in towards negative charges, so that electric field points in like this. The size of those two electric fields had better be the same. Why? Because each of them is going to have a magnitude that's like 1 over 4 pi epsilon naught times their charge divided by r squared. And both of them are the same distance away from that point C, right? There's this symmetry that we can see here. This guy is also going to be 1 over 4 pi epsilon naught, magnitude of Q, right? If I just want the magnitude of that thing, divided by r squared, and those r's are the same in this example. So then to find the total electric field, I just sum these individual vectors, so I'm going to take E minus, line it up tip to tail with E plus, and I see that I get this vector D as the resulting force vector. Okay. All right, let's do another one. So now I have, again, a positive charge and a negative charge, and I want to know what direction will the electric field point at in this point in space represented by this black dot. Okay, I'm going to go ahead and end the poll. Cesar, I see your message that you're not getting the polls popping up on your screen. There's no penalty for that. If you want to keep putting your response in the chat, that's perfectly fine. I'll see it there. Okay, so most of you all selected B. Okay. Let's see if we can agree on that one. So I'm going to go point by point. So let's find the electric field coming from this negative charge here. Over here, I know that that electric field had better point radially inwards towards that negative Q. And, right, so I end up something like this. That's the electric field coming from that negative charge. Let's call it E minus. What about from the positive charge? Well, over here, I know the electric field points radially away from positive charges everywhere. So the electric field is going to be pointing in to the right. Is it going to be larger than in magnitude or smaller in magnitude than the electric field from the negative charges? Well, I know the electric field is proportional to 1 over r squared. So the further I am away from the source charge, the smaller the magnitude of the electric field. So this one better have a magnitude for its electric field that's smaller than E minus. Okay, so I've got these two vectors. I can just put them tip to tail. So I'm going to take E plus, line it up with E minus, put it tip to tail with it, and the resulting vector is this vector B. Okay. I end up with a net vector that points to the left in this case. All right. Okay. Let's try a very similar problem now, but with a bit of increased complexity. So now I have 3 charges, but instead of those charges being located along some common line, they're located at the corners of this rectangle that I've indicated on this slide. And what we want to do is find the net electric field at position A. So I want you guys to help me. What is the first thing that we would do, or how are we going to do? What's just your general problem solving strategy for finding the electric field at position A? What would you think about doing? You can raise your hand and answer verbally or type a few thoughts into the chat. What do we do to get started here? How are we going to find the electric field at position A? Hi, Matt. Do you want to?
First, just get all my units to my standard units. So get centimeters to meters, nanocoulombs to coulombs.
Okay. Yep. That's a good first step. Right. So we know all of these would be, right, all of our nanocoulombs are our 10 to the minus 9 coulombs, right? 10 to the minus 9 coulombs. Everywhere I have nanocoulombs, I can convert that. All our centimeters are like 10 to the minus 2 meters. Okay, that's good. Anybody else? What's another next step? Richie, go ahead.
Yeah, I would draw like vectors of all the forces that are being applied on A from the other particles.
Okay, great. So we could draw the vectors from the, so I think Richie said from the forces, but remember we're finding the electric field, right? So here we're starting by trying to find the electric field. So we wouldn't be finding the forces, but we can draw the electric field vectors for these guys, right? So we can do that quickly. Let's just sketch out what we think those electric vectors are, at least the directions are. So that negative 10 nanocoulombs, it's going to generate an electric field that points radially in towards that negative charge. Okay. That 5 nanocoulomb charge up here, we know is going to generate electric field that points radially away, that say points downwards. And this positive 10 nanocoulombs is going to put some electric field that points in this direction. And let's give them some names. Let's call this one E5 for positive, or sorry, oops, that's not what I wanted to call it. Let's call this one E minus 10 for that negative 10 charge. Let's call this one E10, and let's call this one E5. Right, and so I know what I would do graphically is I would just sum all those vectors together to get the total electric field. Let's try to express, though, the total electric field in some, right, in some way that would be easy to convey without showing a diagram. How am I going to do that? Well, the first thing I need to do is to establish an coordinate system here. So this was a question that I saw in the Slack channel just before lectures today, was basically, how do I know what is the sign, positive or negative, that I associate with forces or electric fields coming from the various source charges or interactions of the electric field with other particles? And really the way to answer that is that it just depends on your coordinate system, right? So a coordinate system is always a free choice. I could define the origin of my coordinate system and the orientation of my coordinate system however I like. And that's just a tool for describing the physical vector or the physical property of that space, right? The vector that I draw doesn't change if I change the coordinate system here. It just changes the components of that vector in my coordinate system. Okay, but that's handy because if I give somebody a coordinate system, then I can define in that coordinate system an electric field using, vector component notation to really concisely convey direction and size of electric fields. So in this one, right, it's always a free choice, but I see that it might be convenient to define one part of my coordinate system pointing up and another part of my coordinate system pointing to the right. We'll call those x and y, and they would be defining these unit vectors I and j, I pointing to the right and j pointing upwards. Okay. So we want to find the total electric field in terms of, right, unit vector I and unit vector j. Okay. I want to find these components. And how am I going to find those components coming from those other vectors that we've drawn there? We drew a vector sort of representing, or just a sketch of what the electric fields look like, coming from those individual charges. And we know we want to do the vector sum, so I need to find, right, say E5, E10, E minus 10, E minus 10. I want to find the vector component notation for each of these. So I want to express all of these in the same notation. So I want to find these components for all of them. Because if I can find these components, right, then summing them up is going to be easy. I know that this guy, the total in I, is just going to be the sum of all these different components that I have before. I'll just add those up, and I just add those up to find that total there. So let's go piece by piece here. So the positive 5 nanocoulomb charge. Let's just first try to establish the signs of the different vectors. So in this coordinate system, will E5 be, does E5 have a component in the x direction? Does E5 have a component in the x direction? What do people think? You can type your answer into the chat maybe. No. Right, let's look. Look, E5 is here it is. It points downwards. There's no component of it that points in the x direction. So I know that E5 has no component in the x direction. So I can just write that as that is 0. What about in the y direction? Is E5 going to be, is its component in the y direction going to be positive or negative? Going to be positive or negative. Well, look, E5 is pointing down. That's the opposite direction of my j hat vector. So what does that tell me about the sign? Okay, I'm getting several of you writing negative into the chat here. Right, this has to be negative because this vector is pointing in the opposite direction of our unit vector j. Okay. What about E10? This is this one that points to the right. So I can see that means that it has no y component. And because it's aligned with my x direction, it's going to be positive in x. Well, what about E minus 10? Is its x component positive or negative? What about the x component, right? I'm looking at this guy. Does this guy have a negative or positive x component? Yeah, look, its x component is going to point in this direction. It points against my I hat direction, so it has a negative x component. Its y component has to point upwards, so it's going to be positive here. So I just, right, set up this problem, right? So these are the steps you should be thinking about, right? This is a fairly straightforward one, but I just want to walk, in detail through these steps. We drew a nice diagram. We used the rules that we've established to draw at least a sketch of the directions of the electric field. Then we defined a coordinate system. And now we're using that coordinate system and our sketch of the directions of the fields to establish the sign of the components for each of the electric fields. Okay. And now we can quickly find the magnitudes here. Well, I know that the electric field is 1 over 4 pi epsilon naught times that charge divided by the distance squared. Right? This is, let's just look at the magnitude of this thing. Something like this. Remember, we also called this k, that 1 over 4 pi epsilon naught. For quickness, I'm just going to use k. So this is like kq over r squared. For the 5 nanocoulombs of charge, right, we just established that there's no component in the x direction. So that means all of that electric field has to point in the negative y direction. So this has to be like k times my 5 times 10 to the minus 9 coulombs divided by, now what's the separation? I want to find the distance between that 5 coulombs and the point A that I'm trying to establish the electric field for. Okay. I can read that off. I see that's 1 centimeter, so this is 1 times 10 to the minus 2 meters, all that squared. Okay. So Devin is asking if k is in all of the equations, can we just ignore it while solving? Yeah, sure. We can just imagine, right? If you want to, you could just imagine that there's a k pulled out in front of all of these terms to make it quick, as long as you make sure you multiply it through at the end to get the correct units and scale. Okay, what do we get for E10? Okay, it's going to be positive. We already established that. Well, I have 10 times 10 to the minus 9 coulombs of charge divided by, now that 10 nanocoulombs of charge is 2 centimeters away. So I have 2 times 10 to the minus 2 meters squared. Now, what about this minus 10 charge? Well, I know the magnitude, right? So here's E10. E minus 10. I know the magnitude of E minus 10 had better be k times minus 10 times 10 to the minus 9 divided by, now the distance, what's the distance that I need here? I need the distance from this negative 10 nanocoulombs to point A. Okay. How far is that? Well, I can use Pythagorean theorem, right? This is going to be 2 squared plus 1 squared square root, right? So this has got to be like the square root of 5 centimeters here. So that distance is the square root of 5 centimeters squared. 5, and then I should put the right units. 5 times 10 to the minus 2 meters, right? So I know the magnitude of E10, but I know that that vector is broken a little bit of it points in the x direction and a little bit points in the y direction. Well, how much points along each? Well, I'm going to observe that there's this triangle that I made that is formed by the vector E minus 10 and its individual components, and that triangle is similar to this larger triangle that's established by the positions of the points that I'm evaluating. And so that means, right, that the ratios of, say, the small side of the triangle to the hypotenuse is the same for that small triangle as it is to the large triangle. And so I can just write down something that I know this guy has to be that magnitude, whoops, let me get a green here. That magnitude of e to the minus 10 that I just calculated below, that's going to be in both of these. And then the component, right, the x component is just going to be something like 1 over, the x component is going to be like 2 over square root of 5, and the y component is going to be like 1 over square root of 5. And I'm just taking those ratios, right? I know that this component is going to be like 1 over square root of 5 by looking at these similar triangles. Okay, and now I'm basically done. Now if I want the total here, I just go through, right, and I sum up these individual bits here. I'm going to get that this is like, right, just 0 plus the x component of E10 plus the x component of E minus 10 to get what I might call, say, EX and EY, right? This is just going to look like E5X plus E10X plus e to the minus 10x, right? Adding up those individual components. Okay, any questions about that? Is it clear how we establish the sign of all of these different components of the electric field? What about the next part of this problem? What about, can we find the acceleration of an electron at point A? How would we do that? How would we find that acceleration? Well, let's just quickly write down this rule. Well, we know that I can generate a force, that a force just comes from putting some charge into an electric field. But I know a force also just describes a mass times an acceleration acting on that particle as well. So I can rearrange this expression to find that the acceleration vector should just be like the charge of some object divided by the mass of some object times the electric field. Okay. Well, that's convenient. Look, this is a vector, just a vector scaling, right? This tells me that the acceleration just looks like a scaled version of the electric field. And so that means that each component, right, if I look at the x component of the acceleration, it should just be like q over m times the x component of the electric field. And if I want the y component of the acceleration, it should just be like the ratio of the charge to the mass times the y value of the electric field. So this thing is a famous thing, right? This charge to mass ratio. You'll hear people, particle physicists or people that study forces acting on objects generated by electric fields are very interested usually in the charge to mass ratio of an object, because that establishes the relationship between the electric field and the acceleration that is experienced by an object placed in that field. And so if I want to write down then the acceleration, the total acceleration, I can again do it in my coordinate system that I've picked here. And I know that this had better just be like the charge to mass ratio qm times Ex times q over m times Ey. Okay, so I can just scale the components by the charge to mass ratio. Now for an electron, right, I would look this up. I would find the charge of the electron and the mass of the electron. And I would find that that q value for the electron is negative. So that negative sign would have to go in here. And that means that the acceleration in the y direction would point in the opposite direction from as the electric field points in the y direction. Okay, let me pause. Are there any questions about this at the moment? Okay. Let's look at another problem then quickly. Let's look at this one. Let's imagine that I have 3 charges and they have different charge built up on them. One has positive Q, the one in the middle has twice that amount of charge, and the one below it has a lower amount of charge plus Q. Here's the question. I want to look at this point in space that's some distance r away from those charges, and those charges are separated by some distance d. Okay. Here's what I want to know. I want to know, what does the electric field look like, or what is the magnitude of the electric field at this point in space if r is much, much bigger than d? So I'm going to imagine this is not drawn to scale, but that r is very, very far away from those point charges, so that d is very, very tiny when I get to those distances here. So let me see what you guys think. Let me stop and relaunch the poll. And you guys let me know which you think is the magnitude of the electric field coming from these charges at some distance very far away from those charges. Okay. All right, I'm going to give you, I might give you 20 more seconds. I see we're still waiting for several people to respond. Okay, let's go ahead and end the poll. So I have a bunch of people responding that the answer is C, and I have a spread of some other answers, and many people did not respond this time. So let's see here. If I want to imagine, right, these charges, right, if are very, right, the D is much smaller than R, right, let's try to draw this a bit more to scale. That means that these three particles, right, are very close together compared to some position over here, maybe position A. And if I were to exaggerate this, right, the more that I change R, right, the larger I make R compared to D, those three particles look sort of closer and closer together. So if I imagine looking at this slide and walking 10 miles back away from this slide and I look in this direction, there would barely be any distance separating those three different charges, right? They would essentially look like they were stacked up just in one single position. So that tells me that this electric field out here better look like the electric field that I would get if I just had 4 units of charge sitting at this position, right? The separation between those charges is so small, right? I'm so far away that the separation between them is essentially inconsequential or unmeasurable. And so if that was the case, if I just had 4 units of charge sitting at a single position, I know the electric field would have 4 pi epsilon naught 4 times Q divided by R squared, worth of electric field, C here. Would it matter, with the strength of the electric field, if I'm very far away, would it depend on which direction I walk? So in this specific example, we moved to the left of that charge distribution. What if I had walked very far away from those charges, like going straight up or off at some angle? What you could imagine is it doesn't matter because the distance scale, right, that separation is becoming so small relative to R squared that I no longer care about that separation distance. So in fact, right, that's also a requirement because those objects better start looking like a point particle field. So at very, very far distances, even though there's some physical separation between those 3 different charges, the field out at very far distances acts like an electric field. And that means it only depends on the radial distance I am away from those charges, right? Not on the angle away from the center of those charges. And right, I can calculate the magnitude just by knowing the sum of all the charges sitting there. This is the reason why we are using this idea that the proton is essentially a point charge for us. Even though in reality, physicists have been able to break the proton into individually smaller charged pieces called quarks, the spacing of those individual charged objects inside of the proton is so small that when you look at it at any reasonable distance scale, it essentially looks like a point charge, that all that charge is packed into one space, even though there is some physical size. Now we have ways to probe down and get and measure and look at a proton at scales where the size of those charges moving around inside of it, right, that are distributed inside of it do matter, and we can measure the physical extent to that charge distribution inside of the proton. But for this class, again, we're just going to take that the proton is a point particle. Okay, any questions about this idea? What's wrong with answer E? This is one you should have been able to throw away immediately. Why could it not have been answer E? Yeah. Nathan is telling me because there's only one R, right? The units would be incorrect here because I don't have a distance squared or meters squared in the denominator. So this one I could have thrown out just by the units. All the other ones have the correct units. Now, you should do this exercise for yourself, right? You could go through and find the individual electric fields coming from each of these three charges, right? E1, E2, E3, take their individual vector components in terms of R and D, and write down an expression for the electric field at that point. And then if you have that expression and you let R become very large, you should find that it becomes essentially, right, it becomes essentially the same point charge. Right, you can imagine how that's going to work, because this thing here, R, right, this thing is like the square root, the size of this distance here is something like d squared plus r squared, square root of d squared plus r squared. But if r becomes very huge, then this d becomes essentially negligible in this distance. And that's going to happen to all of these different charges, that the distance that I am away from it is going to be dominated by the x component of the distance, and this little piece will be inconsequential, right? This term I would be able to neglect it in this expression. Okay, great. So that's as far as I wanted to get today. We're going to pick up with these ideas tomorrow, and we're going to try to extend this to not just a few charges, but we're going to think about lots of charges packed into continuous charge distributions and calculating the electric field coming from those continuous charge distributions. Okay, we've got about 4 minutes left, though, 5 minutes left. If anybody has any questions over anything about the course schedule or the slides or the material we've covered, or anything they read in their book, we can stop and just take questions for the last few minutes here. Are there any questions today? Any comments people want to make? Hi, Nathan.
Can you hear me okay?
I can hear you, Nathan. Yeah, please.
Okay, so this has less to do with what we're learning right now and more with like the course in general. So
Okay.
I read in the syllabus there's going to be 2 tests and they're worth 15% each.
Okay.
I know
Yep.
I know this is kind of a vague question to ask, but on average, how difficult would you say your tests are? Or like how much work would we have to go into preparing for them?
Okay, we will have okay, so thank you, Nathan. So I will provide, when it gets closer to the test, some review materials and problems to work through to give you an idea of what those tests are going to look like. 2 comments about that. One is, how hard will the tests be? I don't really know how hard the tests will be this semester, because I'm going to try to give them in a bit of a different way since we're all working remotely. They'll likely be either some kind of take home or some kind of online version of the test. And that's a very different style than I've given in the past. So I don't have a lot of reference to sort of tell you that. Now, I'm probably going to try to make them as close to what I've done in the past. And typically, my tests are designed to be pretty challenging, I would say. They're designed to test all the core concepts and also see if you've picked up any of the, any of what I've said. Would think of like some of the extended ideas or details of the concepts. That being said, the way I almost always grade tests is on some sort of a curve. So after everybody takes it, I'll try to compare the populations for both sections and establish some fair grading scheme, that distributes the grade in sort of a reasonable way. I don't know. That's about the best I can do right now. I hope I can give you better answers about prepping for the tests and what the tests will look like probably in another week, once I have firmed up exactly the format that those are going to take this semester.
Okay, thank you.
Yeah. Cameron is asking, when is the first written homework due? So the first written homework will be, I don't have my calendar open, but it's posted on the calendar. It's posted in the syllabus. I think it's still a few weeks from now. I think the first 4 chapters are covered in written homework 1, so it won't be due until after we complete our discussions of the first 4 chapters. Will there be review before the exam? The answer is yes, we will have some sort of review session. That might be a week where we'll take the Monday that we don't normally meet and have a review session so that we can talk about any questions you have. And I will provide some material for, right, like a study guide or practice exams for you to go over, so you can have questions for that review. Okay, good questions. Any other last questions?